Hello?
Ed,
Yeah, hello.
hi Ted.
How goes it?
Doing great here. How are you?
Good. Yeah, hanging in there.
I'm just going to test the share screen. Oh, no sharing screen right now.
We have to wait for Bart or Rob.
Can Bart do it on this account?
I believe so. I'm not sure. I had a sudden panic attack that this was going to be a hybrid meeting.
That's all right. I just retrieved Ray from a different room. He was in the wrong room.
Oh.
Those aerospace engineers, they just can't navigate the planet Earth.
Dave,
Yes.
I made you co-host so you can enable sharing.
Oh, okay.
Or, yeah. Rob usually does it that way. I do it differently, so I did it Rob's way.
All right. Let me just check this. Okay. Looks good here. Close this. I hope that's okay.
Evening, everybody.
Evening,
Oh.
Brian.
Brian, you've been busy. I haven't heard or seen from you in a while.
I know it's like I have a real job again.
It's called work.
Been messing with Canon cameras, software for Canon cameras, nonstop. Been working on the app though. When I can, I got some stuff I want to try to get in before the weekend.
That's good.
Yeah, it already looks really good.
Well, thank you. Hopefully this will be a little bit better. I think I am just going to put a button on there I'll get the info from you for whatever the next balloons will be, and that way you could just click it and load it up.
Right. Another thing you could do where you've got the time slot entry, you've got it'll accept any number, and there are no odd numbers. The time slots are on 2-minute increments. So if you wanted to take out the odd numbers, I don't know how much that would help. And I don't know how hard it would be to do.
Not very. I actually did not realize that they couldn't be on odd numbers.
Yeah,
Sweet.
every slot takes 2 minutes. You can't have another slot for 2 more minutes.
See, I'm already learning. You didn't even start yet.
Yeah, that's right. Keep that to yourself.
Hello, everybody.
Hey,
Hey,
Rob.
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 Rob, thanks for those solar cells. Nice job.
I should show you all the dead soldiers I had to go through to get to those.
Yeah, I got a few of those lying around my workplace too.
I finally got the shipment from, I guess, China that I got another 100, so they're slightly bigger.
Uh,
But I'm starting to work on some of those.
Yeah, I put one onto a little cardboard box so we can use it for ground testing. And it's just working out fantastic.
I was actually a little worried because I use 32 gauge wire for the red and the black wires, and I was like looking at the current draw, and I'm like, I really don't know how much that thing draws on. And then you guys are telling me, no, we're not charging the battery. And I'm like, oh, okay.
Yeah, I think 50 milliamps is about what it needs.
Yeah,
No, nothing's going to overheat at that current.
right.
Not at minus 70 degrees.
That's right. I once tested some 22 gauge wire with PVC insulation. I just ran it at 9 amps because that's what I had, and it withstood that. So, a lot of people think, well, even 15 amps, you need 14 gauge wire. But that's the National Electrical Code. They derate so tremendously. But that wire was well within its temperature rating at 9 amps. So I'm not afraid of putting current down wire.
There you go.
Well, Ed, my clock says 7:01. You tell me when we want to start.
Well, I'll call the activities meeting to order and turn it over to Brian to let him run the show. So we are now in session, and Brian.
Do we
comments
need
yours.
anybody with co-host needs for slides or whatever?
I think Dave needs it, right? Does he have it?
Yeah, I think Bart set me up.
Okay.
Yeah. Well, welcome everybody to this evening's activity meeting. I'm very pleased that Dave NZ1J has agreed to give us the skinny on the increasingly popular digital modes. I know there's been a lot of talk about Whisper, and personally, there's a lot for me to learn there, and it seems like there's a lot of people who are interested in the club. So I say this timing couldn't be better. I don't want to take up too much time, though. I'm going to hand it over to Dave and let him do his thing.
Okay. Well, thanks, Brian. Yeah, right now there is a lot of interest in the club with Whisper. Honestly, 2 months ago, I knew next to nothing about it. But Ray and his balloon project is based primarily on Whisper for telemetry. So that got us involved in it. And there's a lot there. And also, it'll bring us into the world of digital communication. And there is an awful lot there. So there's packet radio, there's WinLink, there's radio teletype, there's all kinds of modes. So I've got a presentation for you tonight that hopefully is going to tell you several things you don't already know. So what I'm going to ask is that everybody mutes themselves, but if you have a question or a comment at any time, just unmute and let us hear it, because everybody's coming at this with a different background. So it's impossible for me to tell you exactly what you want to hear. What I don't want to do is tell you something that sounds so foreign to you that you're kind of off kilter. So just let me know if there's anything that you want to comment on or that you want a little clarification or anything like that. So I've got a slideshow, which I will start. Takes a couple of seconds. The little black bar is going to disappear in a couple more seconds, and we should be good. So this is the first slide, and the first question about WSPR is basically, what is it? Well, it tells you right there, Weak Signal Propagation Reporter. So it's an acronym. That's what the letters stand for. So what does that mean? What is a propagation reporter? Well, it's going to work like this. Hundreds of hams volunteer to send out these very weak signals, and hundreds of other volunteers receive those signals. And when they receive them, they send them to the internet where they all get put together. So you can go to a website, and what it will say is, this signal from Connecticut was heard in Hawaii on 20 meters at this time with this signal strength, and the transmitted power was this. So the path of propagation between those 2 points, you know what it is right at that moment. So if you say, gee, can I reach Hawaii on 20 meters at this time? WSPR will tell you, and you can select any band, and it's hundreds and hundreds of pairs of points, because all these amateurs have volunteered to either send out data or receive data, and some people do both. And you can end up with a map of all these possible paths. So these are, and when we say low power, we mean very low power. 5 watts is off the scale for this. Ray's high altitude balloon is using 30 milliwatts, 1/30th of a watt. And he's getting signals out 3,000 miles with that. So this is what it is, a propagation reporter. It's not a communication mode. You can't talk to anybody. All you can do is look at the results. And you can also participate. You can be one of the volunteers that either sends out data or receives data. So what WSPR does, it has a standard format, and all it sends is the call sign of who's transmitting, the grid square that they're in, and we're going to go into what grid squares are because not everybody's familiar with them, and their power level. On the receiving end, they add their call sign, their grid square, and the signal to noise ratio that they received it. And then they send it up to the web. And then you go to a website, and there it all is. And I'm going to show you what it all is. So here is a screenshot from a website, and the website's name is right on the image, WSPR, Weak Signal Propagation Reporter, .rocks. This is not the primary website. This is a secondary website, but they actually did a better job than the primary website. So the primary website, there's an organization called WSPR.net, and they collect all the data and they put it on a website. But I think everybody who's looked at both websites will tell you that WSPR Rocks has a better format. So it's the same information. There's only one set of information, but it looks better. So what we're seeing here, I took a screenshot at some particular time, and I did it on the 15-meter band. They color code the band, so you can see all these lines, the color they're in. That is the color assigned to the 15-meter band. So if you look at where we are here in the eastern United States, at this time, when I took this screenshot, see all these arcs moving from the eastern United States over into Europe? That says, at that time, if you want to have a QSO with somebody in Europe, it's easy to do. All these connections are getting made. Look at all the points in Europe that are marked. But say you wanted to talk to Hawaii, even the West Coast, even California, Japan, Australia, there's nobody making contact over there. So at this time of day on this band, you are going to make these contacts and you're not going to make those. So that's what they mean by propagation reporter. If you ever want to know, if you're on HF and you want to know, can I talk to New Zealand? Can I talk to England? One glance at this website and there's your answer. And you can select what band you want to look at. So I took a snapshot here of the 15-meter band, and here's the next one. This is the 40-meter band. This is the same time I took the two pictures. So you switch to 40 meters, and now it's saying, if you happen to live over here on the West Coast, look at all the connections to Japan. At that time of day, 40 meters is open to Japan, good propagation into Hawaii. But now look, headed over here to the east. Here we are on the eastern part of the US. There are no connections to Europe. So at this particular moment, this is just two data shots, just showing you what information is available there. You could just look at the band and find out what parts of the world are talking to other parts of the world at that time. So what we saw, 15 meters was doing great into Europe. 40 meters, we could make it to Hawaii. If you look at some of these lines, you could see Hawaii is stretching to the East Coast. And you could do this same reporting anytime. So if you go to this website, whisper.rocks, click a couple buttons, you got to say things like, I want to look at the 40-meter band, and it pops right up. And there's the propagation reporter. Now, this tool, which is honestly new to me, it's not a new idea. I'll show you this screen. Here's another website. This is called PSK Reporter, and it doesn't use Whisper at all. It primarily gets its data from FT8. And FT8 is a popular digital mode, so there's lots of people sending and receiving data on FT8. And what you end up with is a diagram that looks basically the same. You're seeing lines that connect transmitting and receiving stations, and I don't remember which band this was on, but you can select it by band. So PSK Reporter is going to give you essentially the same information that Whisper is going to give you, only it's collected through FT8 instead of collected through Whisper. Another difference is PSK Reporter, because it's FT8, there's people here who might be running 50 watts or even 100 watts, and it's not telling you what their transmitted power is. If you took any one of these connections, you don't know if that was a 10 milliwatt signal or a 100 watt signal. Whereas with Whisper, it's all defined. So both very good. So I've been using PSK Reporter for years, and that's why I didn't really go looking for Whisper. But now we found Whisper, a really good tool. So at its core, that's what it is. It's a tool to measure propagation, and there are other tools that also measure propagation. So PSK Reporter is one of them. Here's another. This is called Reverse Beacon. Reverse Beacon primarily is CW. If you look down here, you'll see there is several different modes. So there's CW, there's radio teletype, PSK31. These are 4 different modes that could end up populating data into Reverse Beacon. It's mostly used for CW. So you look here, our own W1DQ, John, I looked him up because I knew he's very active, does a lot of DX. And we look right over here and we find out that W1DQ was heard by all these stations during the time period I checked. He was transmitting at 20 to 21 words per minute. And here's the map showing here's W1DQ, and he was heard by these stations out on the West Coast, one going all the way down into South America, and a lot going into Europe. So what this works really, really well for is testing your own station. But the thing is, for it to really work well, you need to be on Morse code. So if you use Morse code, you get on here, say you put up a new antenna. You just send a CQ message. An automated station picks you up, puts you into the database, puts it on the internet, and you can look it up here and you can say, oh, I'm getting out 500 miles. with this antenna today under these conditions with this power. So this is what I use this mostly for, to test my own station. So this gives us at this point 3 tools: WhisperNet, PSK Reporter, and Reverse Beacon, all of which will tell us about propagation. So they're all tools to help us understand the propagation and make better use of the radio and make more contacts more easily. So now there is the second question. This doesn't look like the right slide to me. Maybe it is. We want to dig a little bit deeper. So at the first level, this is Propagation Reporter, and it's so easy. Go to the website, the data's there, it's in a visual format, and you can find out what the propagation looks like at any given time on any given band. Now we're going to dig a little deeper. According to knowledgeable people, there is 3 different fundamental ways to communicate in ham radio. This is a snippet from Logbook of the World. And I highlighted this. And it says Logbook of the World makes a distinction between CW, phone, and digital. So that's one way to classify communications. 3 fundamental modes. Morse code, which some people say is a digital mode. You could argue one way or the other. Phone, which would be voice of all kinds, AM, FM, single sideband, and then digital modes. And there is a long list of digital modes. And each one has its own characteristics. So Logbook of the World divides it up, and they'll give you awards for any one of the 3. So here I've kind of defined them and given you some examples. And not every ham uses the digital modes. Some of you, it's old hat. You say, oh, I've been doing digital modes since 1975. But not everybody has that. So we'll cover a little bit tonight about digital modes and how they relate to the other modes, CW and phone. The second thing you can do with Whisper, one is you can go to the website and just look at the data, and that's it. It's great. The other thing is you can become part of the network that's producing that data. And to do that, you have to either send out a signal for others to hear or receive signals that others have sent. And because it's digital mode, you need some sort of digital interface. A lot of modern radios have the digital interface built in. And older radios, and maybe some very low-end modern radios, don't have a digital interface. You have to add one. So like Signal Link is a box that you can add to your radio that will enable the digital modes. It allows you to connect it to a computer. And then you need software on the computer to use those digital modes. So some of the modern and popular digital modes get operated through this software that I'm showing here, which is called WSJT-X. And you can run about 7 different modes through this software. If you're already using FT8, and a lot of hams do, then you're already using WSJT-X or some derivative of it, and you already have a digital interface. So, and if you're not, this is the answer to your question, what do I need to do? You need to have a digital interface, and you need to download a free copy of WSJT-X. And this is an image of it running Whisper. This is a frequency that Whisper works on, and these are some Whisper results that have gotten printed out. And I'm going to show you how easy it is once you're set up for digital to go to Whisper. So let's say you do FT8. You go to your WSJT-X, you select mode, and you had been selecting FT8. All you do is click this button for Whisper, and now you're on Whisper. It's that easy. So anybody who's already doing digital, that's all you do. If you're not on digital, you have to get an interface and get some software. And then all these modes will become available to you. FT8 is very, very popular. Some people love it, some people hate it, but you can't argue that it's not popular. The rest of these not as popular, and Whisper is just a reporter mode. So now, moving on, we say, okay, that's Whisper. How did we all end up involved in Whisper? Well, through the High Altitude Balloon Project. The High Altitude Balloon needs a way to send telemetry. So some people talk about APRS, which is a position reporting system. And it has great usability, but it's generally on VHF. And it generally needs comparatively a lot of power. You might need 5 watts or more to run APRS. And because it's VHF, when you're out over the middle of the Atlantic Ocean with your balloon, your signal's not going to get picked up by anybody. So one, to run that 5 watts, you're going to need a lot of power compared to this Whisper transmitter, which is 1/30th of a watt. And when you're out over water, nobody's going to hear you. And when you go over a lot of other countries, they aren't running APRS on the same frequencies we are. So it's really not a good fit for the high altitude balloon. So the high altitude balloon community, which our club has recently joined, settled on Whisper quite a while ago. This has become the standard, and it's because it's very low power and it's very efficient. The signal goes a long way for a very small amount of power. So there's only one little difficulty. Whisper, in its standard incarnation, it only is going to send out 3 things. This is my call sign, this is my grid square, this is my power level. And that's generally fine. You say someone in Connecticut was heard by somebody in England, that's what you needed for propagation reporting. But if you want it to be telemetry, you've got a balloon, you want to know what's its altitude, what's its more precise position, what's the temperature outside, what's the battery voltage. Whisper doesn't have provisions for all that data. It only sends the 3 things: call sign, grid square, and power level. So for high altitude balloons, we need something else. And someone worked that all out for us. But before we get to what the people worked out for high altitude balloons, I want to spend a little bit of time talking about grid squares, because I don't think everybody knows much about grid squares. Grid squares were created like 40 years ago for the VHF community. So if you were going to get on 1 gigahertz and send a signal, you're not going to go 1,000 miles with it. So in order to be something that you can like turn into a contest, you're going to need to be able to say, just like we could say, well, I worked all states or I worked 100 countries. Well, you're not going to do that on 1 gigahertz. Those signals aren't going to travel that far. So you need smaller bite-sized pieces. And you could say, for instance, how many grid squares have I worked on 1 gigahertz? So they developed these grid squares, and it's all based on just latitude and longitude. And it's been around for about 40 years. You may not have run into it because it only has a couple of applications. One is VHF contest work. Another is FT8. FT8, to simplify their data transmission, it doesn't say I'm in Eastern Massachusetts. It says I'm in this grid square. So if you've been using FT8, you know grid squares. And Whisper uses grid squares. So let's talk a little bit about what grid squares are. They took the entire world and they divided it up into rectangles. So the first level of these rectangles is a pair of letters. So if you look here, I'm circling it, you see the big FN. If you trace this red line, this is the edge of the FN grid square. So here we are in Connecticut, we are in FN. So if you said, I'm in FN, that tells you that you're in New England, maybe Nova Scotia, or possibly Pennsylvania or New York. So that's a pretty big rectangle. So that's just the letters FN. They put you inside this rectangle. If you want to know where you are with greater precision, they add a 2-digit number. So I think probably most of us are familiar that we live in FN31. And here it is in blue. FN31 almost perfectly overlays the outline of Connecticut, but it has nothing to do with it. It's based on just degrees of latitude and longitude. So if you say you're in FN31, you say, I'm within this box. So if you're asking what's the propagation from FN31 to England or to Hawaii or to Australia, it doesn't matter whether you're in Eastern Connecticut or Western Connecticut. This grid square is perfectly adequate. So FN31 is in most cases what you're going to hear because it's enough. For high altitude balloons, 50 miles is kind of a rough approximation of where you are. So a balloon might travel 40 miles and it's still in the same grid square. So as far as your indication is, you haven't seen the balloon move at all. So what you want is finer resolution. And the way you do that is by breaking the grid square into smaller grid squares. So you've seen FN as a very, very large rectangle. FN31 is a significantly smaller rectangle. Let's look here. This website will get you the sub-squares inside the typical square. So FN31 would be a typical square. That's what almost everybody refers to when they talk about grid squares. But if you look right here, this is a 6-character grid square. So it's FN31 OL. OL tells us which rectangle inside FN31. So if you can specify your grid square out to 6 characters, you get a box like this one. And I'm hoping you've got enough clarity on your screen. You can see this is essentially Wallingford. So if you say FN31 OL, you're defining a rectangle about the size of Wallingford. You still don't know which side of Wallingford you're on, but you're within just a couple of miles. So with a high altitude balloon, you want to send a 6-character grid square, which normal Whisper won't do that. It sends a 4-character grid square. And as I mentioned, you also want to send temperature, altitude, and battery voltage. So we've got this, and this is a website you can go to, and you can look up anything you like by zip code, call sign, and it'll show you the map and show you where you are. So now this brings us to how are we going to get this additional data sent down from the balloon? And there's a couple of ways.
Dave, I'm sorry, haven't they gone another 2 digits? Because when I was doing satellite stuff, they went, I'm FN31 NL, but there were 2 other letters that I wasn't aware of.
Right, that's true. That doesn't get used for the high altitude balloons, but as you can imagine, what it is another rectangle inside the rectangle. So it's always little rectangles inside larger rectangles. So you've got FN is the largest one, FN31 is significantly smaller, OL is significantly smaller, but then you could take that rectangle, divide it up into about 100 pieces, and that would be the last 2 digits. You're right, to take it out to 8 characters. So it's really a really nice system, and I guess that's why it's been in use for about 40 years. You know, you don't have to use all the characters, and in many cases you don't, but they're available to you. So for high altitude balloons, they've determined that 6 characters is enough. And for satellite work, you go out to 8 characters. And it just gives you more resolution. And I didn't bring up anything in the presentation for the last 2, but thanks for that, Ed. It's true that it will go out even further. And I guess we should look up a map and find out how small that grid square is. It usually goes down to about 10% of the size of the square above it. So if FN31OL is, say, 6 miles across, you add 2 more characters and you're going to be down to an area that's just over half a mile across. That's pretty fine resolution. The system in use for the high altitude balloons adds the 2 characters to give us a total 6, it doesn't have provision to go beyond that. The people who developed it, I guess, determined that 6 characters was enough. So what they've done, I've shown here, this manufacturer, QRP Labs, they have a really, really good product, which is what Ray chose for the high altitude balloon project. And it does all the electronics for a high altitude balloon. It's got a GPS to figure out where it is. It's got a microprocessor to run it, and it's got a transmitter. And it will figure out where it is. Oh, and it's also got the temperature sensor and the battery voltage monitor. So it does everything that the average balloonist wants, and they put it into a very small, affordable package, and they wrote all the software to go along with it. So one of the things they did was figure out a way to get the extra data that a high altitude balloon needs. And they came up with a very unique and interesting way to do that. They created a second WSPR packet. So WSPR, you normally send this packet and you say, here is my call sign, my grid square, my transmit power. And then you go quiet for a long time to give other people a chance to report. And then you come back around and you send it again. So it gets sent out periodically, and we'll get into details later, but periodically WSPR sends out this packet of data. For the high altitude balloon, they want more data. So they came up with this idea, why don't we send 2 consecutive packets? The first packet will have the original WSPR data, and the second packet, we're going to encode different data, the data we didn't get. So the temperature, the battery voltage, and more refinement to the grid square. So here's the problem. There's only so much room in one of these packets. More than half of that room is used up with call sign. And then all you've got left is grid square and power level. So what these guys came up with, pretty clever, you look down here at the bottom, they created a set of illegal call signs. And by illegal, what I mean is there is no call sign in the world that starts with the number 1. So they said, we'll make all of our, not all of our, they picked 3 characters. There's 0, there's 1, and I think maybe Q is the other one. I don't remember. But there are 3 characters that no call sign starts with. So they appropriated those. So they now transmit and they say their call sign is of this format. Now, that's not a real call sign, but they know who you are because you're the guy who just sent on this same frequency in the last packet interval. You did identify with your call sign. The next sequential packet belongs to you, and this QRP Labs, they maintain a database. They know if you bought the board from them, it is encoded with a call sign of this format, and you register with them. I'm flying this balloon under my call sign, and I'm registered with this format. So this illegal call sign is associated with your transmitter. But what it allows you to do is use the call sign for data. So normally you send your call sign, it's the same every time you send it because your call sign is the same every time. What they do, they might send 1K3ABC. Encoded in this is information like your altitude because it's a make-believe call sign, so they can encode information in it. Well, let's say the balloon's altitude changes. They are now going to send a different call sign. It's still going to start with the 1, but some of these other characters are going to change. And this same altered call sign is now going to tell you your new altitude. And it's also got information in it about the outside temperature. So that's the scheme that QRP Labs came up with. They said, let's send 2 packets. The first one's a standard packet. Let's add this second packet. let's put in this call sign, which is unique because no one else in the world can use it, and let's encode data into the call sign. So it's all worked out by them, and it's relatively easy to use. There is some work. If you want to get information out of this, you have to run an algorithm on this to find out, well, what is my altitude, and what is my refined grid square, and what is my battery voltage, because it's encoded in here. So Brian, N1BRI, has written some software that does just that. I'm going to show that to you in a couple of slides. So this is the transmitter from QRP Labs. Their part number for it is U4B, and the 4B would be 4 balloons. They did have a U3B, which they discontinued because they came out with this product, which is superior. So the way this works, this is a USB connector. You connect it to like a laptop computer, which can power it and can communicate with it. And you get it set up for your flight. And then they want you to break the circuit board off right along here, because you say, I'm definitely not going to have a laptop with me when I'm flying. You break the board off here, and the remainder of the board, which is the part that's actually going to fly, it only weighs 2 grams, which is pretty amazing. And you just have to add 6 wires. This pair of wires is your GPS antenna, because there is a GPS receiver on this 2-gram board. And that's what tells the balloon where it is. You got to give it some power, 2 wires over here for power, and you generally hook that to a solar panel. So during the day it transmits, and at night it goes to sleep. But this keeps the weight way down. You don't have to carry batteries. And then these 2 wires go out to a dipole. And QRP Labs has pretty well standardized this all on 20 meters. So this transmitter is going to send out whisper messages on 20 meters into this dipole that you're going to provide. And it's going to use this GPS data. And that is it. If you have a balloon to lift this and a solar panel, it's fine. It's all done. All done, but as Ray will tell you, it's a lot to get everything just right. And everything has to be just right. But they've given us a big piece of the puzzle. So these are commercially available at a reasonable price. They're very lightweight. They seem to be very reliable. They will operate at the negative 65-degree temperatures that you encounter on a high-altitude balloon. And really, all we do is add these 6 wires. So pretty amazing. There are competitors out there. I don't think any of them have a product that does such a nice job, has the mating software to work with it, and weighs so little. And this is one of Ray's balloons being launched. So here is the actual helium-filled balloon. Between here and here, this is the platform that has on it the solar panels and that U4B transmitter board. And in between here is half of a 20-meter dipole. And then if you look down here, you see this little piece of orange tape. That is the bottom of the other half of the dipole. So you got about a 35-foot long dipole. Here in the middle, you got the solar cells giving you power and the U4B board doing all the rest of the work. And this very carefully planned out helium or hydrogen-filled balloon, and that is what you send aloft. So I think most of us have seen a picture of this on social media somewhere along the line, but that's what it all comes down to with high-altitude balloons, which is what brought us to Whisper. So we got Whisper, which is great, and then we got high-altitude balloons, which uses Whisper and an enhancement to Whisper created by QRP Labs to end up with a system where you can launch a balloon at a reasonable cost and get some pretty amazing performance out of it compared to what you could do even 10 years ago. 10 years ago, this particular balloon wasn't on the market, this U4B wasn't on the market, and the software to track it wasn't on the market. And the people who were launching high altitude balloons 10 years ago, they were struggling a lot more than us, and they weren't getting great results. But now, with luck and a lot of due diligence and careful thought, you can have good results. This is a website provided by QRP Labs, and here's their link. Because QRP Labs wants you to be able to track the balloons. So they've come up with this data format, and now you need a way to unpack that data. So they do it for you. The red line is the track of the balloon. So here's the end of the line. That's saying that that's the end of where the balloon is right now. That's how far it made it. And I'm pretty sure the brown was the first loop around the Earth. So this is not our balloon. This is someone's balloon. So it got launched here from Florida. Generally in the northern hemisphere, it's going to move west to east. It went here. It fell off the end of the map, ended up on the other side of the map, went down here. Odd things like this happen with the air currents. Came over here. It changes colors because now it's on lap 2. And here it went around a second time. So this particular balloon, and I don't have the data on whose balloon it was. I looked for one that did extremely well. I didn't want to show you some lesser expectation balloon. But here's somebody's who did a very, very good job. And who knows when it's going to end. This is just where the end of the data was at the time I got it. And so this is QRP Labs, offers this tracking website, and it will show you the track of the balloon. But it doesn't show you the altitude profile. And that's another thing that I think it's just interesting to see. I think everybody agrees you'd like to know what the altitude of the balloon is. So this is free. Anybody can go to this website and you can look at any balloon that's flying and you can look at its track. This is some other software. This is Brian, N1BRI, created this specifically for the Meriden Amateur Radio Club High Altitude Balloon Project. And here's his website. What he's done is put the effort in to make this as user-friendly as it could be and to give us the data that we really want. So here I'm tracking someone's balloon. I just wanted to put some data in there. There's someone's balloon, and I think I only told it to start tracking at a certain time so we don't see the rest of it. But it shows you the track on the map. But also, right here, here's a graph of altitude in feet. So we could track the altitude. Here it is, and it's saying this particular balloon, here it is at about 45,000 feet. And at this point, it probably got heated up by the sun and rose to 55,000 feet. These are big numbers. But this is a great presentation. And down below, here's the calculated speed in miles an hour. So QRP Labs, they did a great job. They offered us an awful lot of stuff. Their tracking website, I don't think it's complete. It gives you a track, but it doesn't tell you altitude. It doesn't tell you speed. Brian can provide us all that and battery voltage. And if we come up with new ideas, he can add that as well. So Brian has been a big contributor to the High Altitude Balloon Project. And he's developed this software, which is available for all of our use, and it gives us really the data we're most interested in probably the most readable format you're going to see. So this wasn't really ready for our earlier flights. We had a peek at it, but it wasn't fully developed. But for future flights, I think this is where we're going to be spending our time. You go to this website, and all the pertinent information is there for us. In a format that's ideal, I think. So here's the recap. This is not the recap of the whole presentation. This is the recap of part 1 of the presentation. And what I've got here is a bunch of websites that you can look at, and it will give you pretty much all the information you need. So whisper.rocks, that's probably the one that you want to look at first. And if you just go to Google and type in Whisper Rocks, it will take you here. And that shows you what Whisper will do. For balloon data, you want to go to either the QRP Labs website or to Brian's website, u4b.live. And I put something down here for WSJT because that's the software you need if you're not into digital modes and you want to get into digital modes. And I can put some of these into the chat so I can share them with you. But I'm wondering if you really need that. It's Whisper Rocks. It's U4B.live. And it's WSJT. Those are the three things. Those three are going to tell you everything you need to know. You can also take a screenshot right now. They're sitting right up here. And of course, ask any one of us, Ray or me or Brian, and we give you all the details you want. But I would say these three websites, that covers it. Whisper.rocks, U4B.live, and WSJT. Okay, so the second half is going to get more technical. And I happened to notice no one had any comments or questions so far in part one. Also, I did discuss with Ray.
I beg your pardon. I had a question. I had a comment.
Oh, no, better than that. You had a comment, which was even better, and I appreciate it. Yeah, and I don't know how that slipped my mind, and I apologize. So before we go over to part two, which you're going to find duller and drier than part one, if Ray wants to interject, because I know a lot of people in the club are very interested in the high altitude balloon project, I tried to stay focused here on just the radio telemetry aspect of the project. But Ray, if there's anything you want to chime in about the project itself, that would be great.
Sorry, it took me a second to find unmute. I'm going to say a few things. Dave, first, this is a great presentation. You're really sharing a lot of information. And one of the primary goals of the balloon project was simply to have it be educational, for the club and anybody interested. And I think it is truly proving to be that. It was also meant to build camaraderie and for folks to have a lot of fun, and I think we all are. At this point, we've done 2 launches. Our first one, we overfilled the balloon where we were in the field. We wanted to make sure we would get up over the trees, and we did. That flight lasted about 6 hours. It reported a lot of very, very good data to us. We got very, very anxious. When we got to the second balloon launch, we got to a point where we worked out probably to within half a gram the exact amount of gas that we needed to fill the balloon with. And in fact, when we let the balloon and that platform go, that launch from a balloon standpoint was picture perfect. The balloon rises at only about 1 foot every second. So it's a nice, slow, steady ascent. But as with everything, our luck held out for quite a long time. And actually, the failure that we experienced with the second launch actually turned out to be very lucky for us. As the balloon left, we completely lost contact with the balloon itself. And what we discovered was we did have a software issue with the platform that we had generated, and its ability to come up or wake up when the sunlight hits it. And that was, I don't want to say a failure for us, but we found a point of concern. We have fixed that now. I think we're well on the way of testing that for the third launch. But this really isn't about the balloon launch. It's really about Dave's presentation. So Dave, take it away.
Okay.
Can I just ask one quick question? What is so important about a slow lift of the balloon? Is it mechanical stress on the board?
No, Ed, you opened the can of worms now.
Yeah, all right. So I'll give it to you in 3 easy steps. You want the balloon to launch at some reasonable rate. If it launches and rises too slowly, there's a chance when you get up into the clouds that it's going to build up a lot of condensation. And at those temperatures between 50 and minus 70 degrees Fahrenheit, it's going to freeze. The balloon is going to start coming back down. It's going to thaw. It's going to rise back up. You can pick just about the right amount of lift, which should get you through cloud cover if we get that high fairly well. If it rises too fast, the balloon's basically going to expand too quickly and the balloon is going to burst. All right. And so that's why we have to hit just those right parameters. And it's been, I think we pretty much knew what it was going to be when we did the first launch. We chose not to obey that rule because, we were in a park and we really wanted to make sure that we were going to get a launch. The second launch, we hit right on the button. We don't know how long that balloon is, but that balloon could still be up there. For all we know, we have no way to know it. It's got a fully functional platform. It's just, given the software glitch that we have, it works when you let it go. It just won't restart itself every morning. And so that's where we are now. We're ready to do that final test.
And is the
Ray.
balloon launch seasonal? I mean, do you launch it differently in the summer than in the winter?
Here's another can of worms. We're going to take a little bit more time away from your presentation, Dave, and I apologize for that. You got to look at a number of things. The first thing is the platforms we're launching now have our solar cells horizontal, all right? And so the sun's rays are hitting it at a 90-degree angle. They're going to be most effective. They will give us whatever voltage and current they possibly can most effectively. And with solar panels, it should be noted that the colder they get, the more efficient they get, up to 20% more efficient. So the problem we have is we picked a voltage that on the ground, the board and the system would operate. But when we get to minus 70 degrees Fahrenheit, if we hit that plus 20% efficiency, we don't want to over voltage the board. And we don't want to put a regulator on there and weigh the platform down, because we're just talking literally fractions of grams so that they're all adding up. As the seasons change, Earth's position with the sun, et cetera, changes. And so that angle to the horizontal lessens and lessens and lessens. And as it does, you get less effective radiation hitting the panel, all right? And so you don't get effectively the voltage and the current you want. Now, the good news for a launch is we can control that in the summer and say, we're launching in the summer, everything's rosy, we're gonna get the best effect that we possibly can. What we never know is where the balloon is gonna go. So if the balloon travels around the Earth, okay, about where we are, position of the Earth, we're in pretty good shape. If the winds take that balloon, say, up towards the North Pole, it is possible, even in the summer, that some morning the balloon's just not going to wake up, and it may not wake up for a few days, and then suddenly it will again when we get the right radiation hitting, pattern hitting the balloon. But we can watch the balloon, we can see where it is. If we lose contact and we can figure out what that angle is, we might know that the balloon just doesn't wake up for a day or two and then does again when it comes back. So that's the short answer.
What's the longest the balloon of the type you're launching can stay up there?
It could stay up for weeks, maybe a month or so. That's all dependent on a lot of things. We've cheated this system one other way as well. Right now, we've taken an inexpensive approach and we're using a mixture of helium and air. John, MFU, has been nice enough now he will share some of his pure helium with us. And so as we do future launches, and we put 99.9 or 99% helium in the balloon with no air, we should hit a fairly good altitude, maybe close to around 40,000 feet, and we should be able to stay in orbit for much longer.
I got a question. Do you have a picture of that transmitter compared to something like a quarter or something like that, just to get a size? And also a comment, that eight-digit grid is used for rescue work, like beacons in airplanes and ships and things like that.
It fits in a teaspoon, Al.
Yeah, we do have a picture. Dave, I don't know if you have one tonight or not, but
I don't have it handy.
Yeah. Okay. We'll get it to you. And in fact, I'll send it to Dave Sweedock and see if I can get him. He's going to post something about the balloon. I'll see if we can get him to post that as well. But the company posts a standard picture. They have a teaspoon, and this board fits well within the confines of that teaspoon.
Yeah, the total weight of what you fly is 2 grams, and 29 grams makes an ounce. So
Yeah.
you're below 1/10 of an ounce.
Yeah. So when we're done building the platform, attaching the cord and wire for both ends of the dipole, the GPS antenna, all of that without the balloon comes in, and I'm going to round it to about 20 grams. All right. And so when we're done, we've got to get the balloon to inflate and be buoyant on its own. Then we've got to get the balloon to be able to lift the 20 grams. And then we've got to give it some additional amount of lift so that balloon will rise at some given rate of speed.
Two quick questions, Ray. What software or hardware did you use to record the data from the first balloon launch, and how high did the balloon get?
The balloon, well, the data was all tracked on WhisperNet, so we did nothing special there at all. And in fact, that day in the club, we were using QRP Labs. How high did the balloon go? Dave, I'm going to guess that when we averaged that out, it was about maybe 28, 30,000 feet for that.
Yes,
flight.
that's right.
Yep. So,
And that's where it essentially sprung a leak due to overpressure.
yeah, and we knew that. We had overfilled the balloon to get it off the ground safely. So, and you could watch it. It was a slow leak. That balloon did not come down quickly. It came down over about a 2-hour period of time, and it looks like it came down in a fairly linear fashion as well.
Right.
And I have no idea what fish might have eaten the board. But all right, Dave, why don't you get back to what we're here for?
Okay, thank you, Ray.
Yep.
Well, the second half, like I said, it's deeper, it's drier, and we got theoretically 7 minutes left. But I think any of you who know presentations I've given in the past, running long is something that happens. So for anybody who has the fortitude to go on, I'm going to share my screen again, and we'll look at what's now actually part 3. So when you read the slide that says it's part 2, Ray gave you part 2. This is part 3. So I'm going to click this and this. Okay, so this is where we left off. So we said that is Whisper, and that was what we billed the presentation as. But I talked with Brian, and we agreed that Whisper is very interesting, but it ties in with a bunch of other very interesting things. There's a lot of digital modes available to ham radio, and some of us use them, some of us don't. Some of us use them and don't really understand them. So we're going to try and dig into the technical details of digital communication a little, because it's a big subject. So here we are. This is part 3. Let's take a look at the idea of analog and digital. A lot of people don't even use the word analog. They say digital to emphasize that it is digital. If it's not digital, it's analog. So analog means it can take on any value at all. So you might have 1 volt. You want to transmit 1 volt and get some receiver somewhere else in the world to receive that 1 volt. But because it's analog, it can take on any value. So you could send 1.000001 volt, and that's just a different voltage. Every voltage is allowable. The problem with that is, if I put out 1 volt with my transmitter, and it picks up some noise, and noise is everywhere. Noise is inescapable. You can minimize noise, but you can never eliminate it. So you send out your 1 volt, and it picks up 1 microvolt of noise. The receiver hears 1.000001 volt. It doesn't know that that's not what you were trying to send. You tried to send 1 volt, and the receiver received something slightly different. And it can't know which is the signal and which is the noise. It can't. You can eliminate some noise, but not all of it. So therefore, analog communication is error prone. And anybody who remembers back in the day, and the average age of hams tells me that most of you remember back in the day, if you went to a photocopier and you made a copy, and then you handed that copy to somebody and they said, oh, this looks interesting, I'll make a copy. And that happens about 5 times. The copy that comes out looks pretty bad. And the reason is noise. You went through the photocopier and a little bit of noise was introduced. You take the copy and you put it through the photocopy, it introduces more noise. And this goes on, and the noise just builds up. And a little bit of noise, which you say, okay, I can live with that. Once you do it several times, it becomes unacceptable. Same thing would happen. Somebody tries to make a copy of a VHS tape. The quality of the copies just keeps getting worse and worse. That's the analog world. Digital offers us a lot of advantages. And Most of those advantages were not available to us until recently because you need modern electronics in order to take advantage of digital communication. So we have old school digital communication like radio teletype, which is good, but it's not as good, nowhere near as good as modern digital communication, which takes advantage of all kinds of digital processing. I think most of us have heard of DSP, digital signal processing. A lot of modern radios come with digital signal processing built in. And I think most people agree that you're getting a radio that does a lot more than a radio of 20 years ago because they've digitized the system. So this concept of digital communication is a means of really greatly enhancing communication. So I've got an example here that you have a car that can travel at any speed, but a digital speedometer is only going to tell you certain ones of those speeds. For instance, 30 miles an hour or 31 miles an hour. Speedometer in your car is not going to tell you 30.1 miles an hour. A different digital system might be designed to tell you to the 10th of a mile an hour, but even if you did that, it's not going to tell you to the 100th of a mile an hour. There's always a limitation to digital. The limitation is actually one of its strengths, and I'm going to get into why that is. And here's the big thing. Digital communication can be perfect. You can never say that about analog communication. It can be perfect. You could take an MP3 file and you can send it over the internet to somebody and they can send it to somebody, and you could do that 10,000 times. And the last copy of that MP3 file is perfect. And you can never do that with analog, but you can do it with digital. Here's why. Here's a sense of why you can. So here I'm giving you this example. If you have an analog signal and it's supposed to be 1 volt, but noise, there's always noise, turns it into 1.01 volt. Well, the receiver hears that and says, 1.01 volt, that's what you sent me. The noise, the error, is now built into that signal, and you pretty much can never take it out. But here's what you do with a digital system. You say there are allowed values, and anything else is not an allowed value. So let's say you make a system that you say, I can send you 1 volt or 1.1 or 1.2, etc., always on a 10th of a volt. Those are the only legal voltages. Now somebody sends you 1 volt. It becomes 1.01 due to noise. The receiver says that had to be 1. It was nowhere near far enough to be 1.1. So that 0.01 volt of noise is eliminated at the receiver. It takes the signal plus the noise and says, this was the signal, and it throws away the noise. So with an analog system, you never throw away the noise. With a digital system, if you're doing things properly, you can always throw away the noise. So this is one of the big things. Perfect communication through digital means. Not every digital means is perfect, but it has the potential to be perfect because you can design the system to do a lot of different things. So for instance, if you look at a JPEG image, JPEGs are lossy, which means if you had a picture that you started with, and it's very high resolution, it's very high quality, you convert it into a JPEG, you have knowingly, willingly, intentionally lost some of that data. That is a lossy format. So what they said was, I want to take this picture and put it into a small amount of data because big amounts of data are hard to deal with. And they're saying, but I'm willing to put up with some loss of precision. The image isn't going to be perfect anymore. So that is a digital mode, and it's not perfect, but that's the way it was designed. They said in a JPEG image format, what they said was, I want a small file. They said, we'll give you a small file with an acceptable amount of loss. You could also design a system to be perfect, but you can't compress the data like a JPEG and have a perfect image. Can't get both. Stop me at any time. This is going to get drier and tougher as we go.
Let me say, I have a comment.
Oh, yes, John.
There's a zone of uncertainty between one digit and another digit.
Yes, right. And the idea is if you make the gap between those two digits a certain size, and the noise moves you, let's say, 1/3 of the way, the distance between those two, you can rightly assume that the nearest digit is the digit you take. So that's the general idea behind digital communication. To make
Hey,
it
Dave.
work, yes.
So in that example you gave about the 1.1, 1.2, et cetera, to make that work, don't you have to have an idea of what your noise is going to be?
Yes, you do. And every digital system is designed a little differently. So what you have to do is figure out how much signal you're going to have and how much noise you're going to tolerate. And the way it works, like if you're using, let's say you have Dish Network for your television, you're getting a digital signal down from Dish Network. And all kinds of things can happen, and you get a perfect picture. It's absolutely perfect because the system was designed to work under the conditions that it's working in. But you get a day of the heaviest rainstorm of the year, and you suddenly lose your picture completely. The picture doesn't get fuzzy. It doesn't have a little bit of snow in it. It just vanishes. That is another one of the natures of digital systems. Here's the problem. If I say I can send you 1 volt or 1.1 volt, if the noise never exceeds 1.03 volts, I know that 1.03 goes back to 1. But let's say the noise goes as high as 1.08 volts. Now it looks like 1.1, and there's an error. So the system has to be designed to work within the amount of noise you expect to have. And they can and do fail. So Dish Network on a very rainy day, it fails. But up until the point it fails, it's correcting its own errors. So you can have perfect transmission up to a point. What you can't have is an unlimited amount of perfect data through a very noisy channel. So you've got to make design decisions. And people have done that. For every communication scheme that's in use, somebody made decisions as to what is the best way to do this. So for instance, you could say 1, 1.1, and 1.2 are all valid voltages. You could also say 1, 2, and 3 are all valid voltages. The difference is, if you want to go from 1 volt to 3 volts, you're going to need more power. You're going to need a bigger signal level, which naturally improves your signal to noise ratio. So you're getting around the additional noise by using additional power. But it's got to be designed to work under the conditions that it's going to see in real life. So a group of really smart people did this with broadcast over-the-air television around the year 2008. It got released. And look at the 3 things that happened. They took the analog television system that we had, and they ended up sending us a better picture using less power and less bandwidth. So that's an advantage of a digital system. With the technology of the 1950s, we had analog television. It served us for 60 years, and it was good enough. But you could get snow, you could get ghosts, you get the color wasn't stable. When they went to digital, all those problems went away, and less bandwidth and less transmitted power. But to make this all work, modern microprocessors are the workhorse. So like digital signal processing uses very powerful microprocessors. They're kind of custom-made microprocessors to do digital signal processing. They are the equivalent If you talk about filters, in an analog system, you take a 1950 radio, and all you had was three things: capacitors, inductors, and crystals. And out of those three things, you're going to do all your tuning. You're going to do all your filtering. Everything's going to be done with capacitors, inductors, and crystals. If you rely on capacitors and inductors, which you use for most everything in a radio, you take a radio apart, it's got some crystals in it, but it's got a lot of capacitors and inductors. Every time you make a filter and you put in either an inductor or a capacitor, you call that a pole. That filter has a pole in it. And the more poles you put in a filter, the better the filter is. And back in the day, if you had a 4-pole filter, that was considered a pretty good filter. That means you put in like 2 capacitors, 2 inductors. With digital signal processing, you're not actually putting components in there. You're using software to do mathematics on the digital signal. You can get filters easily that are 1,000 poles. So picture the performance you could have with 4 poles, which basically means 2 capacitors, 2 inductors, to the performance you could have with 1,000 poles. And now that we've gone digital, 1,000 pole filter is easily made. And they put them right inside your radio. And now suddenly you could set a CW signal, you can set a 50 hertz wide filter with what they call sharp skirts. It very abruptly changes from I'm receiving these frequencies to I'm rejecting those frequencies. Abruptly, sharply, and narrow. And they're doing it by digitally producing what would be a 1,000 pole filter. So you just needed the theory was there. People had worked out the theory 100 years ago, but nobody could build it. But now we have the microprocessors, and now we can build it. So there's been a revolution in the last 20 years in radio communication, which includes broadcast television, because we've gone digital. So now, digging down another level below all this, so we say digital, and we kind of have a sense that digital has discrete levels, but now we have to deal with those discrete levels. So now we're going down to really the basics, the concept of binary numbers and the concept of a bit. Probably everybody's heard of bits, bits per second, bits and bytes. A byte is 8 bits put together. You probably heard bytes more than bits. A bit is 1 binary digit. So in our number scheme, we use decimal digits because we have the decimal number scheme. Computers are not very good at dealing with decimal. They want to work in binary. So next couple of slides, I'm going to try and give you a primer on what is binary and what is a bit. And if you don't like any of this, then maybe it's time to take a little break. So here's our concept. The decimal number system we use, we have 10 symbols, and the symbols are 0 through 9. And we can count any number we want using those 10 symbols. So at the bottom of this screen, I've shown that a decimal number 9 in our decimal system, which sometimes we don't even call it the decimal system, it's how we count, it's the same as a binary 1001. So we're representing this number 9, which is 9 in decimal, as this binary number. So the next slide is going to help shed some light on this. I know a lot of you are thinking, oh yeah, binary, I know that. And you do, but not all of us do. So I'm going to wade us through this. So I'm going to give you this rule that I doubt many of you have heard, but this rule will let you count in any number system. You just need this one rule and you count to wherever you want. So in computers, there is binary, and there's a couple of other number systems that are in use. One is called hexadecimal, which probably isn't as widely known as binary, and binary is not all that widely known. And there's another one called octal. And it's all based on the number base. And the number base is how many symbols do you have? So decimal, like decade is 10, decimal is 10. So that means we have 10 symbols. And the 10 symbols in the decimal number system is 0 through 9. So here's the rule I'm going to give you. You have been doing this since you were 2 years old, but you've never said it like this, I'm expecting. Here is the rule for counting. Start with your first symbol, which would be 0. Go through all your symbols one at a time. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I've used all 10 symbols. When you run out of symbols, go back to the first symbol and carry a 1. So we are at 9. 9 goes back to 0. And we carry a 1 and we get 10. So you've been doing it. Everybody's been doing it. But you never said it like that. So there's the rule. Go through all your symbols. Go back to 0 and carry a 1. So let's see what happens here in binary. Let's look on this page. Look at the binary. So we start with the number 0, and we can represent it as, I'm going to represent it as 4 zeros. But 4 zeros is no different than 1 0. It's 0. There's 0. The rule is go through every symbol you have. So in decimal, we go to the next symbol, 1. In binary, we go to the next symbol. It's 1. Let's count again. In decimal, we go to 2. It's the next symbol. How many symbols do we have in the binary system, like bicycle has 2 wheels? We have 2 symbols. So we use 0, we use 1, and the rule is when you run out of symbols, go back to 0 and carry the 1. The 1 goes back to 0, and we carry the 1. So this 2 is represented by this number, which you read this as 1 0. But this is how you count in binary. And in fact, this is how you count in any number system. So if I gave you numbers in octal or hexadecimal, using the same rule, you can count as high as you want. The rule is simply use up all your symbols and then carry. That's all you do. So let's count just a couple more. There's 2. We go to 3. Well, this is 0. So we go to the next symbol, which is 1. And we already had this one. So we read this as 1 1. That is the equivalent of number 3. Count one more. Here's the number 4. So here's the rule. There's no more symbols after 1. Go back to 0. Carry a 1. Well, I have 1. If I carry a 1, I don't have a symbol for that. So I go back to 0 and carry the 1. And there it is. 4 becomes 1 0 0. And if you follow that rule, you can count as high as you want in any base system you want. Hexadecimal, octal, binary. So,
Hey, Dave,
yes.
the way I always say, I see your rule, which I never knew that. But the way I always counted with the binary would you start all the way over to the right, and that digit is a 1,
Right.
value 1. The next column moving to the left, you double the 1, and that becomes a 2. Then the next digit over, you double the 2, that becomes a 4. You double the 4, that becomes an 8. So if you go down and look at, say, your number 5, the first digit was a 1. Then the second digit would be a 2, but there's nothing, it's 0. You double the 2, that would be a 4. So you got a 4 plus 1, that equals 5.
That's absolutely right.
But I never knew your
right.
the official rule, but that's how I always just did it.
Well,
in my head.
and the method you're using is another excellent method. And they don't contradict each other in any way. It's 2 ways of looking at the same thing.
Yeah.
In fact,
that's how I always did it when I had to set dip switches on things, you know. So anyway, yeah, just thought
that's great.
It's easier to understand for me.
Right. This is a different perspective, and I'm going to build on what you just told us, and I'm going to introduce the double dabble method of binary to decimal conversion. And I'll bet you not many of you are familiar with the double dabble method. And here is the double dabble method. It works as simply as this. You start on the right, you take that number, it's 1. Every time you move to the left, like Jim said, you double it. So there's 1. When I get here, I now have 2. Oh, you know what? I started at the wrong side. You have to start at this side. Let's start at this side. I have 0. I move to the right, I double it. It's still 0. But now I have a 1, so I add the 1. Now I have 1. I move to the right, it becomes 2. There's nothing here, so it's still 2. I move to the right, 2 becomes 4, and I have a 1. 4 and 1 is 5. There's the answer. So you can start, if you start on the left, with any binary number, no matter how long it is, double dabble simply says, every time you move to the right, you double whatever you've got, and every time you see a 1, you add it. That's the only 2 things you do. Every time you move, you double it. Every time you see a 1, you add it. And when you get to the end, you will have the answer. And it's based on what you told us, Jim. It's based on the idea that every column is double the one next to it. But it's a very quick method. If you're ever presented with a 12-digit long binary number, you can start on the left and you can come across, and you'd be surprised how easily you'll get the decimal equivalent out of that. So right now I would call that trivia. But since we're running long anyway, give you some trivia. So here's the idea of binary. You need a bit, which is a binary digit, and we are going to take numbers expressed as binary and send them out over the radio digitally. So really, in its simplest form, all we have to do is send something over the radio that represents a 0 and something else that represents a 1, and we do it in sequence. So we would take, let's say, a millisecond to send this character, and then another millisecond here and here and here, and on the receiving end, you'd have the number. And at its basic, that's the idea of digital communication. So we have to use binary, so I just wanted to give a little introduction to binary. And for digital communication, everything becomes a binary number. So if you want to send the letter A, there is no binary equivalent of A, because A is not a number. You could take a decimal number like 9, you could turn it into a binary number, because you're representing a number in a different number system. But the letter A isn't in a number system. So what you have to do is assign a number. So down here at the bottom, we're saying there is a pretty standard format that gets used an awful lot called ASCII, which is the American Standard Code for Information Interchange. And it's been around 50 years or so. And they define that the letter capital A becomes the number 65. And then the number 65 gets converted to binary and looks like this. So if you had the understanding that you're sending ASCII encoded data over the radio, and then you sent this binary number, the person on the receiving end would say, oh, you sent me the letter A. The same thing would be true if you're using slow scan television. You would have to take the picture elements, which people call pixels, and you'd have to assign numbers to them. And the number would represent the brightness and the color. And you would have to have the understanding on the receiving end that what you're receiving is a slow scan television signal. And then you would get that data and get those numbers and turn it back into brightness and colors. The next thing that digital communication needs in order to be really good is this idea called compression. So you come away from tonight with this idea that in good digital communication systems, they use compression, and here it is all in one little phrase. Compression means using fewer bits to do the same job. So I talked about a JPEG image earlier. The JPEG image, if you ever put a bitmap file on a thumb drive and you put a JPEG file of the same image, the JPEG file might be 5% the size of the bitmap file because they use compression in the JPEG file. And compression lets you use fewer bits to send the same amount of information. So early systems like radio teletype, which go back 70 years, they didn't do really any form of compression because they didn't have the technology at the time to do it. Modern digital communication counts on compression as one key part of it. So here's this idea that maybe a lot of you have never seen before. You're going to compress the data before you transmit it, and you're going to end up using fewer bits to transmit the data. And I'm giving you an example here of how you might do something like that. For all of this, there are much more sophisticated examples. The people who have developed modern digital communication have really dug deep, and they have unearthed pretty much every trick that can be used is pretty much in use now. So I'm trying to give you simple examples of the concept. So binary data, digital data, let's start. Digital data first, binary data, and now compression. And then error correction, which is another idea that allows modern digital communication to work so well. So here's the basic idea, and here's a very simple way to do it. Sending a message 3 times. So if I sent you a bunch of digital numbers, one of those numbers might be wrong. There might have been enough noise that one of the numbers is wrong, which means what you received was a distorted message because one of the numbers is wrong. If I sent you the entire message from start to finish 3 times in a row, and you compare them at the receiver, and you say, of these 3 sets of data, 2 are the same and 1 is different. Well, for a reasonable amount of noise, and this goes to, I think it was Jim's comment, that if you get too much noise, the whole system falls apart. If the noise is manageable, so that you only get an occasional error here and there. Got these 3 copies, 2 are the same, they must be the correct ones. The one that's different must be the incorrect one. If you go to too much noise, all 3 of them could be incorrect, and now you can't fix it. So you have to stay within the amount of noise the system is designed for. But there's always going to be noise. There's no getting around it. And noise is random. So what you could have is noise is acceptable 99% of the time, but 1% of the time that noise pops up a little bit more and you get an error. This error correction will fix those few errors that slip through. So here's a simple example, and I told you, the people who've developed the modern digital systems, they do a lot more math than this to get the results they want. But this is an example of what you could do. Send the data 3 times, compare all 3 sets, pull out the right answer, as long as your noise stays within bounds. So 2 new ideas to add to the digital communication. First, compression, and then error correction. And Whisper uses both of those. So here are Whisper messages. The Whisper message is very regimented. This is it. You're going to get a call sign, a 4-digit grid square, and a power level. And that is it. They take this, which if you send it in ASCII, which I'd mentioned a couple of slides back, standard format, ASCII would say that every one of these characters would need 7 bits. And if you count up all the characters, including the spaces, and you multiply by 7, I don't know what that number is, but I know it's a lot more than 50. So to get this data down to 50 bits, you use this method called compression. You compress the data, and you use mathematics on this set of numbers to take this larger set of data and squeeze it down to the smaller set. So that's one of your jobs. You take a digital message and you compress it. So Whisper does that. And these are specifics about Whisper. Here's the format of the message. Here's the first step. You compress it. Then you add the error correction, which by its nature, it expands it. And I said in my example, we might send the data 3 times. Well, look how much the expansion goes. 50 bits becomes 162 bits. They're using a more sophisticated method than I mentioned, but their method of sending more data than you started with allows for error correction. You can find and fix the errors at the receiver. And here's a couple of more details that I think most of us are going to find this to be really kind of surprising. This one I love. The bandwidth of WSPR is 6 hertz. The bandwidth of single sideband is around 2700 hertz. And this is 6. So you talk about narrow bandwidth communication. 6 hertz, this message could go through. So you could send hundreds of WSPR signals all inside the bandwidth of a single sideband transmission because it's so narrow band. And look how slow the data is. 1.5 bits per second. Now I had said here, if I want to send a letter W using ASCII, that is 7 bits. And I'm only sending 1.5 bits per second. So that says on average, to send this letter W, I need 5 seconds to send one letter. So picture you're sending Morse code, 5 seconds per letter, which works out to about 30 seconds per word. So you're sending it 2 words per minute. That would be the equivalent Morse code speed. And there's a reason for that. And I got it on a later slide. There's not that many more slides. The general rule, another takeaway from tonight, the general rule, the slower you send, the more noise you can withstand. That is a given. You just keep slowing down and you can get through more noise. So WSPR, which is designed to get through a lot of noise, they slowed down to 1.5 bits per second, which works out to about 2 words per minute of Morse code. So here's some examples of speeds and signal to noise ratios. FT8 is, as I'm sure everybody's heard of it, whether you've used it or not, whether you like it or hate it, you've heard of it. FT8 is our standard. Let's take a look at the whole list. FT4 is a quicker mode than FT8. You can send, here's where I am, and here's my call sign. You can send that in 7 seconds. On FT8, it would take you 15 seconds to send the same information. And FT4 can withstand less noise than FT8 because you're sending the signal more quickly. And therefore, you can't stand as much noise. So this can stand the least amount of noise. This goes slower. You can stand more noise. JT65, look how much slower that is. And it will work with an even weaker signal or more noise. Either way you look at it, it's signal to noise ratio. So you can have a weaker signal or more noise. Either way, it's going to affect your signal to noise ratio. JT65 will get through where FT8 won't, and it'll get through where FT4 won't. And WSPR 2, the 2 means it takes 2 minutes to send a packet of data. It can get through under conditions that JT65 can't get through. And there is a mode that almost nobody is using this mode, but there is a WSPR 15 where they take the same packet that they were sending here in 2 minutes, and they're going to spend 15 minutes sending the packet. And the rule is the slower you go, the more noise you can withstand. So WSPR 15, which I've never seen an example of anybody using it, but the standard does exist. It will work in the face of even more noise than any of the others. So there's your hierarchy. The faster you send it, the less noise you can withstand, or the more power you have to put in your signal to overcome the noise. WSPR 2, I think most of us were very surprised when we got our initial results back with WSPR 2. We're sending out 1/30th of a watt, and we're getting it received error-free 3,000 miles away. So that's a pretty good benchmark for digital communication. And I've got this little anecdote I put down here. Probably most of you have read this by now. So this is 1965 technology. So here's Mariner 4 It's at Mars, maybe 50 million miles away. They take these handful of pictures and they got to send them back by radio to get that data, which was at the time digital data. This was NASA. They had a big budget. They're sending digital data back in 1965, and it took 9 days to get the data back. Because what's the rule? The slower you go, the more you can get a signal through the noise. So you send a signal 50 million miles, when you receive it, it's going to be a pretty weak signal. So they're using monstrous receive antennas. They're using every tool they've got at the time. But to make it work, and work reliably enough so they were sure it's going to work when they get to Mars, that was what they slowed down to. 9 days to send 21 low resolution black and white photos. So that's a slow data rate. So I'm trying to put the fine point on this, that with any digital communication mode, no matter what else you do, the slower you go, the more noise you can withstand, or the lower signal level you can use. So there is still more, 4 more. So we're all pretty familiar with amplitude modulation and frequency modulation, and probably most of us have some understanding of frequency shift keying. Frequency shift keying is the digital equivalent of FM. So FM says frequency modulation. We're going to take the carrier and move its frequency around, and that's how we're going to send information. Frequency shift keying says, I'm going to do the exact same thing. I'm going to take the carrier and move it to various frequencies. Here's the difference, and I know probably most of you are already saying this, but I'm going to say it for you. FM, you can move the frequency anywhere. You could take a 100 megahertz signal and move it to 100 megahertz plus 10 hertz, or plus 1 hertz, or plus a half a hertz. Because it's analog, you can move it to anywhere. Frequency shift keying is digital. You define what the available frequencies are. So for instance, radio teletype, it's an old system, so it's going to use old technology. They use 2 frequencies, and they shift the frequency of the carrier between these 2 frequencies. There are no other allowed frequencies, just these 2. And all your receiver has to decide, am I receiving this frequency or this other frequency? So you have old style analog filters, 1 filter at each of the 2 frequencies. If one filter gives you a signal bigger than the other filter, you say, well, I'm receiving, say, a digital 0. And if it's the other filter that's giving you the biggest signal, you say, I'm receiving a digital 1. And that's really all there is to it. So radio teletype, an early, by today's standard, not very sophisticated communication system, but for what it is, it works very well. But I do want to add this one other little tidbit. Whenever we modulate, which means essentially put information onto the carrier. So that information could be digital data, could be Morse code, speech, slow scan television images. The modulation is putting the information onto the carrier. You could put it on 3 ways. You can change the amplitude of the carrier, and that's called amplitude modulation. You can change the frequency, which is frequency modulation if it's analog, and frequency shift keying if it's digital, or you can change the phase. And there is a communication mode, I don't know that it's as popular now as it was 20 years ago, called PSK31, phase shift keying 31. And there was a time it was very popular. It allowed you to do keyboard to keyboard digital communication. So you could be typing in a message to somebody and they're receiving it in real time while you're typing it, and then they could send you one back. So you could have a digital QSO in real time, which is something you could do with other modes now, but I just mention it because it's an example of phase shift keying. Because I don't think phase shift is used as often as frequency shifting and amplitude. So here's 3 examples of modes that all use frequency shift keying. So radio teletype, it goes back a long, long way. FT8, which is much more modern, and Whisper, which is also modern. And the list of digital modes is really quite long. But here's 3. They're all popular. They all use frequency shift keying. There are other modes. If you get digital television, that's called quadrature amplitude modulation. So they decided, based on the constraints they have for sending broadcast television, that quadrature amplitude modulation was the best choice for them. And what we're finding is, for most of our digital modes, frequency shift keying is the best choice. And it all comes down to trade-offs, and there's a lot of math for somebody to figure out which is the best method. But you've got to figure the people who did this knew what they were doing, and we've got an awful lot of digital communication modes that are very, very powerful. So here's a quick run through of radio teletype. It is probably the simplest digital communication mode, so it's worth taking a look at so you don't get buried under details of the more modern systems. So it's early, but it's good. It's still in use today. There's radio teletype contests a couple of times every year. Characters are sent serially. Serially means if I have 5 bits and I want to send them to you, I send one, and when I'm done, I send another, and when I'm done, I send the next. So that's serial communication, one followed by another. The opposite of serial would be parallel, where you would send them all at once. And by radio, there are ways to do that, but they weren't really good enough to be used when radio teletype was developed. So they're sent serially. They only use 5 bits because they're using this thing called the Baudot code, which only uses 5 bits rather than the 7 bits of the ASCII code. And it uses frequency shift keying. It uses 2 tones, and it fits in a bandwidth of 300 hertz. And it will send you 60 words per minute. So anybody who's a typist knows 60 words per minute on a typewriter is pretty darn good. So here's this very old radio teletype system, and you're receiving data at 60 words per minute, which one of the reasons it didn't go faster is the mechanical typewriters of the day couldn't go any faster. So that was the choice they made. So it's still a good mode. After 70 years, it's still good, still in use. And it had limitations both because of the mechanical typewriters and also the electronics. There was only so much you could do back in the 1940s to send digital communications. But now we have modern electronics. And for ham radio, we have this name, Joe Taylor, K1JT. There's Joe Taylor right in his call sign. And you may have noticed the package you use to receive most of these advanced digital modes is WSJT. Well, here's the JT in WSJT. So Joe Taylor, he's a physicist. He just kept cranking out new modes. So he created JT65, and there's the JT again. He created JT9, and then he collaborated with some people. And that's when you started to come up with FT because of the collaboration. But he's really the spark plug behind all of this. So he developed many of these modes. And we're kind of wrapping it up now. So to get modern digital communication better than radio teletype, we're going to apply compression, which radio teletype does not do, error correction, which it doesn't do, and we're going to go to more than 2 tones. So radio teletype only had 2 tones. But if you're trying to build a radio receiver in 1950, you probably didn't want to build filters to identify, let's say, 65 tones. JT65, which is a modern mode, 65 different tones get sent, which means you need excellent filters that can identify and isolate each one of those 65 tones in order to receive the signal. So you go back to the days of radio teletype, you weren't going to do that. You were going to use 2 tones, and you were going to live with the results. One of the other rules with frequency shift keying, I told you, the slower you go, the better your signal to noise ratio is going to be. Another rule is the more tones you use, the better your signal to noise ratio is going to be. But this has diminishing returns. 4 tones is clearly better than 2. 8 tones is only a little bit better than 4. And by the time you get to 65 tones, what you find out is you're kind of wasting your time. And that's why JT65 is an older mode than FT8. So they tried the 65 tones, and I think, I don't know for sure, but I think they kind of learned from that. No need to go to 65 tones. So FT8 uses 8, and Whisper, it only uses 4 tones. But 4 tones is better than 2. So you've got they're all excellent schemes. FT8, FT4 is every bit as good as FT8. It's quicker, so you know it's not going to give you as good a signal-to-noise ratio, but it's almost as good, and it's quicker. So for anybody who has never tried digital modes, it's worth at least taking a look. Go into the club station on a Saturday morning and see what you can learn about some of these modes, because there's only 3 ways to communicate according to some experts, and that's CW, phone, and digital. So if you've never taken a look at digital, it's absolutely worth a look. There is things there that are useful and fun for the radio hobby. So these modern modes are very nearly ideal. They've done the math. They've used the digital signal processing to build systems that can use that math. And as I said a couple of times, you end up with send out 30 milliwatts and hear it 3,000 miles away. And pretty much the only way you're going to do better is to go slower. So there is something like Whisper 15, which can go slower and give you a better signal to noise ratio. And I don't know just about anybody who's using it, because you're kind of at the limits. So there you have it. There's a lot there. You take from it whatever you could. If you want to dig deeper, this is the club to do it in. And there is a dozen digital modes that could all be investigated. So we started with Whisper because the balloon brought us to Whisper, and it allowed us at least a smattering of these other digital modes. And I like FT8. If you want to do Earth, Moon, Earth, FT8 is an excellent choice, because your signal to noise ratio over the 500,000 mile trip to the moon and back is pretty low. And FT8 gets your signal through. Before FT8, people would put a 1,000-watt amplifier on their transmitter, hook it to 64 antennas, bounce it off the moon, and hope on a good day they could hear it come back. Now you could send 100 watts instead of 1,000, put it on 4 antennas instead of 64, use FT8 and its signal to noise capability, and get the signal back. So look what it's done for Earth, Moon, Earth communication. It made it from virtually no one is going to do that to, if you have a mind to, you can do it. So I'm sure that was more than enough.
Well, that was a tour de Dave, tour de force.
Can we
Thank
all
you.
stand
It
and
was,
applaud?
yes,
Can we all stand and applaud? That was the best presentation I've probably seen in a long, long, long time, and I know he put a lot of work into it. Dave, thank you.
Thank you.
Yeah, thanks, Dave.
Thanks very much, Dave. Really appreciate it. And just so you guys know, I just came sort of off the cuff and asked Dave if he'd be willing to do something, and he came right back and, clearly stepped right up. So as always, when he's not, I don't know where he finds the time between answering all the questions that I have. I'm constantly badgering him with, but I'm glad, and I think we're all lucky that he's a member of this club. So thank you very much, Dave.
Thank you.
I have one question for you, Dave.
Okay.
Do you happen to know what happened to JT9 mode?
I don't.
JT9 came before JT65, I believe, and I don't think too many people use that mode at all.
Yeah, and I think JT9 was 9 tones.
Yeah.
I don't know what it was specifically designed to do, but I know it goes back at least 20 years. And I don't know, I have to look into it. There's so many modes. Honestly, 75% of the digital modes I don't know much about. I know there's one that looks like a facsimile. It draws you a picture of the letter they're trying to send you, and you look at the picture.
Telschreiber.
Right.
And that was
Right.
invented by the Germans to do to send faxes during World War I.
So, and with these days, you can download free software. Any one of these modes, you can download free software. And as long as you have a digital interface, you get on the air and give it a try. And for the popular modes, there are contests. And you don't even have to participate in the contest, but that guarantees you there's people on the air sending that mode. You could just go into receive mode and just receive it, get some idea. That's how I started with JT65. I just received. I just listened and saw what was going on. And when I was just coming up to speed on JT65, FT8 came out. And about 3 months after FT8 came out, you go to the JT65 frequency and it's dead. Everyone abandoned it because they said, do I want to send a 1 minute message or a 15-second message? And they all ran to FT8. The JT65, you're not going to hear much over there anymore.
And Dave, how come FT4 isn't more popular than FT8?
Well, one is you're giving up a little bit of signal noise ratio. And the other is it's hard to keep up with. With a 15-second transmission, you have 2, maybe 3 seconds to do whatever you've got to do to respond because it's two-way communication. And if you don't start at the 15-second cycle, the cycles are all regimented. If you don't start at the right time, you don't send the full message, which means your signal noise ratio suffers. FT8 it's kind of laid back. You've got 2, maybe 3 seconds, and you can react. FT4, I've only used it a little, and I had to race to keep up with it. I know Bob, KC1AU, he's got more experience. Bob, what do you think of FT4?
You got to be right on it.
You have to be very quick. You got to know what you're doing and be quick at it. But I found I can, work everyone I can hear pretty quickly.
It's more for contests.
I think
Definitely for a contest.
I think the reason why digital modes go out of use is popularity. For example, PSK31 used to be very, very popular. It used to be the weak signal digital mode, PSK31. And then when FT8 came along, PSK31 just died. You still hear it, people still use it, but because of FT8, and when the next thing comes along, maybe FT8 will disappear.
PSK31 is still very active. It's used for rag queuing. I've been in the digital modes starting with radio teletype back in the 80s, and I'm still using it. I love it.
I've been around a long time. I've been licensed for 7 years. I operate CW because I enjoy it. When I went to FT8, I could appreciate a great advancement in signal to noise at a sacrifice of information being transmitted back and forth. And it left me with a feeling that I didn't need any skill to do FT8. I needed skill to do CW. I still feel that way, but trying to not be an old stuck in the mud.
Well, John, I've seen memes of 3 guys sitting in front of computers and radio sleeping, and the caption reads, "This is our FT8 team." The computers are doing everything, and they're just taking a little snooze. So you're absolutely right. It does not require a lot of skill or effort, and CW definitely does. And they both have a place in our hobby. If you think the band is dead, you tune to the FT8 frequency and see if you still think it's dead.
That's true.
You look at the spotting, it's all FT8.
I like that PSK31. I still do it from time to time. It's kind of like instant messaging, except you don't need the computer. You know, I have a QRP rig that natively decodes PSK31. So I hook that up sometimes. I just put a keyboard into it. It's got a little interface. I'm chatting. It's pretty neat.
All these modes, it's worth taking a look at them. You know, if you haven't at least taken a look, there's like a third of the hobby, right? You get CW, phone, and digital. So I think it's worth everybody's time to at least take a look. And in the club, you don't have to own the digital interface. You don't have to install and configure software. Just go to the club on a Saturday morning. The equipment's all there. Have a look.
Okay, Brian, thank you very much for your coordinating this. Dave, thank you so very much for your knowledge and your ability to communicate. Ray, thank you for being a balloonist and adding all that, and thank everyone else for their attention. It's impressive. We had a total of 23, and 21 stayed through the all three presentations. So congratulations to the members of the club as well.
Well done.
If there's no other business, I will entertain a motion to adjourn.
Made.
So moved.
Second.
Okay. Any opposed?
Okay.
There you go.